Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. So in the last lecture I talked about the scattering phenomena, which is fundamental to various nanoscale photonics. So in this lecture I would like to talk about plasmonic resonance. Okay. So and as I was mentioning previously, essentially plasmonics is the science of interaction of light with metals. Okay. The metals play a key role in this. Okay. And before I go into the details of what plasmonics is, I just want to get some terminology out of the way. Okay. So basically there are different types of plasmonic resonances people talk about in the literature. Okay. And I'll show you what those are in a moment. So to understand what these different types of plasmonic resonances are, we'll have to look at Maxwell's equations, and we can do some mathematics, basic operations algebra on that, and we can obtain an expression which is shown here. Okay. So this will be there in any textbook, and I really don't want to get into it. So I'm just giving the expression. So essentially this is a vector equation. So you have the k vector. That means that wave can be in any direction. It's not having any of the three coordinates. And then electric field also is three-dimensional. And then you have the permittivity and then the omega square. Okay. So if you notice, this is a bit of a advanced thing, but just for sake of accuracy I have put in here the epsilon. If you notice here, it has a k dependence. Okay. This is basically an advanced thing which we call as non-locality in the literature. Okay. What essentially it means is that well, the epsilon can even depend on the size of the structure, but this is only applicable when the structures are very, very small. For example, I think of thin films of less than 1 nanometer or so, or nanoparticles of that scale of less than nanometers. Okay. If the object is of the size of nanometers, then we have to worry. If it is not, then we don't have to worry, and we'll actually simply call it as epsilon of omega. So epsilon only depends on the frequency that we have seen last time. Okay. So just this is just for the sake of clarification I had put in here. Okay. So yeah, this equation is valid. Okay. Now to classify the various type of plasmonic resonances, we consider whether the wave is transverse or longitudinal. Okay. What do I mean by transverse wave? For example, first let's consider the transverse wave. Okay. When we say transverse, we essentially mean that electric field is perpendicular to the direction of propagation. So essentially k dot E equal to 0. Okay. These are the transverse. K is perpendicular to E. So when you have such a scenario, then essentially the relation above gives you a simplified dispersion relation, which is k square equal to epsilon of omega. So I'm removing the non-locality part. So let's forget that right now. And omega square by c square. Okay. This is the generalized dispersion relation for transverse wave. So any of this electromagnetic radiation we are talking about, we are only talking about transverse waves, right? Electric field is perpendicular. So when you have such a scenario, what happens? Well, as I said, plasmonics is science of interaction of light with metals, right? And we know metals dispersion relation is given by 1 minus omega p square. I'm considering an ideal metal. Okay. So 1 minus omega p square by omega square divided into omega square by c square. This is k square. So if you rearrange it, quickly you will see that omega square equal to omega p square plus c square k square. Okay. So when you have metal, let me pick right here. So when you have light interacting with metals, we have a different dispersion which is given by this here. What does it mean? Well, we have already seen the regular light line, the dispersion for plane waves, right? So wherein we talked about k omega versus k relation, and we said that light essentially is this particular line, omega equal to ck. This is a familiar electromagnetic wave which is propagating in free space. But when you think of a wave which is interacting with metals, the dispersion is now modified. And how is it modified? At k equal to 0, there is this omega doesn't go to 0, or rather, but it becomes omega p. So if you plot this relation, it will effectively turn out to be something like this. Okay, so this is my omega p square. Okay, what it means is that this essentially is what we call as a plasmon dispersion. Here, this I'll call as plasmon dispersion. What essentially it means is that these can exist only at omegas greater than the light, omega ck. They cannot exist below omega equal to ck. All right. So this is what we call as, generally in the literature, this type of waves wherein you have transverse electromagnetic waves interacting with metals, we call them as surface plasmons. Okay. Again, there are many subcategories in this. When you talk of a surface, when it's interacting with a nanoparticle, we call it localized surface plasmon. When you have interaction of light with interface of metal and dielectric, we call it, the wave propagates, so we call it surface plasmon polariton, and so on. These are the different terms that we see in the literature. Okay, this is for the transverse waves. In addition, you can also have longitudinal waves. Okay, what do I mean by longitudinal waves? Wherein you basically have k is parallel to E. Okay, when you have such a scenario, your dispersion on the left side in the equation here, if you see on the top, the left side becomes 0. Essentially, your dispersion becomes epsilon of omega equal to epsilon of omega square by c square equal to 0. The trivial solution is no frequency, right? Omega equal to 0. This is valid. Another non-trivial solution is basically this equation will be satisfied when epsilon of omega equal to 0. And we know that in metals this happens at plasma frequency. If I take my ideal metal, epsilon of omega equal to 1 minus omega p square by omega square. At the frequency of plasma frequency, when omega equal to omega p, the epsilon goes to 0, and you can actually excite what are known as bulk plasmons. Okay, these are known as bulk or volume plasmons. All right. The interesting thing is these are longitudinal waves and they cannot couple to the regular electromagnetic waves. If I shine light on a metal, I cannot excite a bulk plasmon. The reason is the incident wave, electromagnetic wave, is transverse, and so it cannot excite these bulk plasmons, but they can be excited. Back in the olden days, in 60s and 70s, when plasmonics was in the nascent stages, people looked at what happens when you shine electron beams on metals, and they looked at their energy loss spectroscopy and things like that. And in those experiments, wherein you are actually you have an electron beam, E-beam irradiation, then you can excite these bulk plasmons, and you will see that. Okay, at the plasma frequency, you will see this plasmon getting excited, and so you have an absorption peak. Okay, but in the regular case, we don't. All right. So this is just for the sake of academic interest, that I mentioned, and we will not really get into the bulk plasmon part in this course. Okay, we will only focus on the surface plasmons, which are essentially interaction of transverse electromagnetic waves with metal structures. Okay, this is a bit of a clarification. So now, this is a very interesting case. Okay, the simplest possible plasmonic effect that you can see. Okay, wherein I am considering an electromagnetic wave which is incident on a metal nanoparticle. What happens? Okay, so to simplify my life, initially I make what is known as a quasi-static approximation. What I mean by that is, let's say if I have my electromagnetic wave, it is basically, let's say it's oscillating in a form of sine wave like this. Okay. I'm sorry. I have a sine wave like this. What I'm essentially assuming is the electric field over the nanoparticle is going to be constant. Okay. So I'll represent my electric field in this direction. I'll call it E naught. How can this happen? Electric field all over a nanoparticle is constant. Well, this is the wavelength, right? If I have a wave like this is going to be my distance is going to be wavelength lambda, and suppose my particle is very, very small compared to, this I'll call it as, let's say, d. The size of the particle is d, and it is much, much smaller than lambda. then effectively the particle will experience a constant electric field. Okay, so this is known as a quasi-static approximation. So essentially electric field, E field, is constant over the across the nanoparticle. Okay, so now what happens when you have such a quasi-static approximation? This is the simplest problem that you would have solved in electrostatics rather. If you, let's say, take a look at a book like Griffith's, which is an Introduction to Electrodynamics. I think chapter 3 has a section on this, where they solve how a metal particle or metal sphere interacts with a constant electric field. Okay, the important thing to recognize is this electric field is constant at any particular instant, but over time the electric field can keep sweeping or switching rather. So you'll have at one moment like this, another moment after it will be out of phase, right, and back and forth. The electric field keeps switching direction, but we are assuming that at any particular instant it is constant across the nanoparticle. Okay, so what do you expect? Okay, instead of talking about the time behavior, we'll take this constant electric field because it gives us a lot of insight. Okay, so now when you have such a scenario, the electric field will of course cause the electrons to move, right? So it will cause a separation of positive and negative charges. How will they charge? For example, electrons will move to the minus direction, and then positive charges will accumulate on the right side. Okay, so when you have such a dipole, we essentially are creating an induced dipole. Okay, so excuse me. So when you have a field constant like this, it essentially leads to induced dipole. Okay, because of the separated positive and negative charges. Where are the positive charges coming from here? Well, they are the nucleus. When you have the electron cloud, which is basically distributed, it's very slightly shifts to the left, and then there is a positive nucleus, which is essentially the background, which is causing a so effectively you can think of let's say a sphere, nuclear sphere like this. I'm sorry. Yeah, well, it became an oval. Let me try to make it a circle. So essentially you have the nucleus, which is, let's say, in black here, positive, and I have my electrons which are slightly displaced from that. Okay, well, you have, I exaggerated this. So effectively this is my negative charge and this is my positive charge. When such a scenario happens, there is this induced dipole that is created because of the net positive and negative charges, and there is an electric field, induced field, right? So within the nanoparticle there will be a induced, E induced. And how much is this E induced? E induced, you know how much? Well, if you look at the basic electrostatics, we know that the electric field inside the metal has to be 0. Why should it be 0? Well, if it is not 0, the electrons will move and rearrange in such a way that electric field becomes 0. So therefore, at any instant of time, E induced is going to be equal to minus E naught. So essentially inside the nanoparticle, the electric field is getting cancelled out. Outside you have the field, okay? And then of course you have this dipole that is created, basically this positive and negative charges that will cause, and that dipole is changing in time, so that will cause radiation, alright? So this is the basic idea, alright? So now what happens, okay? So if you, let's say, go and look at Griffith's textbook, he'll show you that, okay, you can take, basically you can solve this problem in terms of spherical polar coordinates. Okay, he solves, he gives the entire derivation. If you have basic mathematical physics, you can actually follow. It's not that difficult. If not, well, the final answer of all the analysis is that there is this polarization, or this dipole that is created. We call it polarization, and that is essentially given by this expression here on the right. So the polarization charge is, there is some expression, and there is this epsilon 1, which is the metal's dielectric permittivity, and epsilon 2, which is the medium, background medium. Okay, so when you have such a scenario wherein I have this epsilon 2 and this is epsilon 1, my metal, so the surface charge is going to be given by this. Okay, and the interesting thing here is the surface charge, previously I have drawn as plus and minus. Why did I not put any surface charge here? Within the volume of the metal, the electric field has to be 0. There is no charges. Okay, but at the surface you can have, because there's a boundary condition, right? You can have charges. So for example, why don't we have charges like this, positive and negative, on the top and the bottom surfaces? Well, the reason for that is essentially you know that from Maxwell's equation, the tangential component of the electric field is continuous. Okay, so electric field inside is 0 here, and the tangential component has to be continuous. So electric field here also has to be 0. You can have surface charges only when there is a jump in the electric field. So there is no charge on the perpendicular direction. Only along the direction of the electric field you have this charge separation, and that is what is captured by this cos expression here. When you see this, the cos theta essentially tells you that the charges are getting separated along the electric field, and if you go in the polar direction, along the polar direction, the density reduces. Okay, so here my density of charge or induced charge reduces in polar direction. Okay, so now what else? Well, you see that there is this nice term epsilon 1 plus 2 epsilon 2, and we have already seen something interesting happens whenever the denominator goes to 0. So now what happens when epsilon 1 plus 2 epsilon 2 equal to 0, or equal to or close to 0, let's say? What happens? Well, polarization exhibits a resonant response, right? So basically this polarization exhibits, what do you mean by that? Well, it just means that the surface charges are going to become very, very strong. There's large amount of this plus and minus charges that is created whenever epsilon is equal to epsilon 1 equal to minus 2 epsilon 2, whenever this equation is satisfied. How can this happen? Well, it happens because, again, going back, we know that epsilon 1 equal to I'm considering an ideal metal, or rather if I take a druid metal, it will be omega p square by omega square plus I gamma omega. This is my permittivity. Okay. If I take an ideal metal, it will simply be 1 minus omega p square by omega square. Okay. So now what happens when omega is less than omega p? The expression becomes negative. Epsilon 1 becomes negative, and therefore you can have a scenario wherein at, let's say, okay, what is the condition for the resonant response? So 1 minus omega p square divided by omega square is my permittivity of the metal. I ignored the loss for now. Plus 2 epsilon 2. Epsilon 2 I said is a medium, so let's consider that as air. Okay, epsilon 2 as air, so 1. That is equal to 0. This implies my 3, right? 3 and omega, this goes this side. So basically omega equal to omega p, omega square equal to omega p square divided by 3. Okay, so this is a characteristic frequency. So, and we'll call it we'll give it a name. We'll call it surface plasmon frequency, which is omega p divided by root of 3. At that whenever you have a plasma frequency of a metal, and roughly at this distance, okay, omega p by root 3, it essentially becomes close to 1 or close to minus 2, and that's why it becomes resonant. Okay, just remember that this is for an ideal metal. If you take, I'll give you an example problem in the either in the homework or in the exam. So wherein I'll ask you to calculate for, let's say, a real metal. I'll give you, let's say, maybe I'll give you this, instead of 1, I'll give you an epsilon infinity. Okay, I'll give epsilon infinity minus omega p square divided by omega square. What happens to the plasmon frequency? Okay, you just find out where the denominator goes to 0, and that's the resonant response. Okay, for a more real metal. All right. So if the denominator is going to 0, does it mean that the surface charge becomes infinite? Okay, does it mean the charge accumulated on the left and the right becomes infinity? Well, it does not. Okay, the reason is that we have ignored the the imaginary part of the metal, right? Because there is this gamma term here. In this case, there is this gamma, which is going to limit the amount of charge. Okay. Finally, you will see that in the denominator, there is going to be a gamma, and because gamma is never truly zero, there is a finite amount of surface charge that you are creating. Okay. And this particular resonance is known as localized surface plasmon resonance. Localized surface plasmon resonance, LSPR. Okay. So what happens in this at this LSPR? Well, if I actually look at the way, let's say now instead of epsilon, what happens when epsilon is positive? Let's say dielectric, right? If I take my sphere to be, in this case, epsilon, let's say, sphere, right? This is, let's say epsilon is 3. When you have epsilon equal to 3, a dielectric, which is, possible, right? I can think of a dielectric which has an epsilon of 3. If I have such a scenario, what will be my surface charge? There is still this polarization that is created on the surfaces, but that is going to be roughly equal to 3 epsilon naught into 3 minus, let's say 1, which is 2 divided by 3 plus 2, 5 into E naught cos theta. So when I have this kind of a scenario, I'm going to have a very small amount of surface charge. Okay. If I have a dielectric, but instead, if epsilon equal to 3, if I have epsilon negative, let's say minus 2, if I assume, then you'll see that the surface charge is going to blow up. Okay. So what does it mean? This is the exact, the way it looks is captured by this schematic here. So essentially consider a situation wherein you have, let's say, electric field in the positive direction. You will see that if you put a negative epsilon here, the whole polarization turns out to be negative. There's a phase lag in this. At the resonant frequency, there's a phase lag. And because of that, you will see that there are these positive and negative charges that are coming in. All right. And similarly, as the wave changes, you go to the negative part of the, when the electric field reverses, then you have positive and negative, this oscillation of electric field which happens. And that is what we were calling it surface plasmon resonance. Okay. And this localized surface plasmon resonance, LSPR. So basically charge density oscillation is out of phase. All right. You'll see that there's a negative term that comes in. All right. So that's why it happens. Out of phase with driving field. And if you go slightly out of resonance, slightly, close to, let's say instead of being at omega naught at the resonant frequency, slightly away from it, there will be an additional phase lag that is being captured by this term phi. All right. So this is how the plasmon resonance looks like. All right. So I'll stop this lecture here. And in the next lecture, I'll talk about how to excite these surface plasmons and so on. Okay. Yeah. Yeah. There's a question, Saurabh. Yeah. What is it? Can you stand up and speak, please? I can see you. Yeah. Yeah. Oh, well, the question is a plasmonic resonance related only to gold? Because everywhere I'm showing you this gold. Well, I don't have that much of affinity to gold, but yeah, any metal, any noble metal will work. The idea is that if you looked at the second week of lectures, go back and review the dielectric permittivity, you will see that for gold and silver, the loss is quite low. The gamma factor that I'm talking about, right? The gamma factor has to be small. So I said epsilon is going to be epsilon 1. For a metal, it's going to be epsilon infinity minus omega p square divided by omega square plus I gamma omega. So this gamma is capturing the loss in the metal. Okay, this is a collision rate effectively, and the collision rate we saw was about less than 50 femtoseconds, right? Collision time is less than 50 femtoseconds, so rate is something. Okay, so if you compare different metals, you will see that the gamma factor is smallest for silver first, and then gold. The problem, I can also use silver to get these plasmonic resonances, but silver sulfidizes. When you expose it to atmosphere, it sulfidizes, and because of which it doesn't work very well. Okay, that's why we end up using gold typically. That's it. Okay, all right. But gold and silver are the most prominent plasmonic materials. Yeah. Anything else? If not, okay. All right. Thank you so much. I'll catch you in the next lecture, wherein we'll talk about, as I said, how to excite these plasmons and what are the size dependencies. All right. See you then. Thank you.